Heisenberg's uncertainty principle. Probably most of us will remember from various science classes that every particle has a wave associated with it. So for a particle in one-dimensional space, for example, the wave function looks like the sinusoidal function that I have here. Now suppose that I'd like to locate this particle in space. The wave function of a particle at a well-defined position is a sharply peaked function with zero amplitude everywhere except at the location of the particle. So let's look at this graph. For example, this is a one-dimensional world, the x-axis, and this axis here shows the amplitude of the wave function. So this peak here, right at this x, is where the particle is located. Now let's keep this in mind for a moment and look at this picture that I have borrowed from this reference here. Now what we have here is several sine functions. For example, this is one, here's another one, and here is yet another one. So if we superimpose all these sine functions, we get something that looks like this one here, the one in bold black color. And what it shows us is the approximate location of a particle, which we show with delta x. Remember that each of these sine functions can be the wave function of some particle in this one-dimensional world along the x-axis. Now let's go one step further and look at this top part of this figure. What we have done here is we have added a lot more sine functions and we have superimposed them. If you do so, you will end up with even more pronounced peak. You'll see it's much narrower, which means that we have a better idea about the approximate location of the particle. Now, let's go even further and use infinite amount of sine functions, which we represent here with this shaded region. If we do so, that is, if we add all these sine functions, infinite number of sine functions, we will end up with a spike on the x-axis. Now, what does this mean? It means that we have localized the particle, that is, we know exactly its location, or in other words, the uncertainty in x is 0. Okay, so we know where the particle is, but what was the cost of obtaining the location? The cost was we used infinite number of sine functions, and each one of these sine functions represents a different momentum of the particle. Curvature is related to the kinetic energy, that is, to the momentum of the particle. So to summarize, we have lost all our information about the momentum of the particle so that we can find its exact location. Now this is what we call the Heisenberg's uncertainty principle, and it can be derived in a more formal mathematical way, and here is what you get if you go through that math. It just means that if we multiply the uncertainty in the position of the particle with the uncertainty in its momentum, we will get something that's equal or larger than h bar over 2. Here h bar is the Planck's constant divided by 2 pi. This basically tells us that if we have large delta x, we have small delta p, and vice versa. Or if you go to one of the limits, let's say where delta p is 0, then we get delta x to be infinite, which means that we have no idea about where the particle is if we know its momentum. Here's a famous joke. So what you see here is Heisenberg riding his car, and he's driving pretty fast. So a police car is chasing him, and at the end the police catches him and stops him. And one of the policemen asks, "Sir, do you know how fast you were driving?" And Heisenberg very calmly replies, "No, but I know exactly where I am." Now, if we have Heisenberg's uncertainty principle, how come we can determine the position and the speed of Heisenberg simultaneously? That is, why don't we see in our ordinary lives this uncertainty principle? The answer becomes clear if we look at this formula more carefully. What I've done here is I just put delta x and I rewrote delta p in terms of mass times uncertainty and speed. And let's look at this formula. If the mass is a mass of a macroscopic object, this number here becomes very, very small. That's because this is small and we are dividing by some very large number. We get very small delta x, that is very small uncertainty in the position. So if this was the mass of Heisenberg, this delta x here would be practically negligible. And here's an example. If we know the speed of a 1 gram projectile to within 10 to the minus 6 meters per second, the minimum uncertainty in its position will be 5 times 10 to the minus 6 meters. So even for a 1 gram projectile, this uncertainty is negligible. However, for the same uncertainty in the speed, that is this 10 to the minus 6 meters per second, the uncertainty in the position of an electron is far larger than the radius of an atom.